To navigate the human body with engineering precision, we need a standard coordinate system. We define these using anatomical, planes-fixed, imaginary surfaces that slice through the body to describe location and movement. If you don't master these, you can't accurately describe where a force is acting or where a prosthetic needs to align. The sagittal plane, the forward-backward axis. The sagittal plane is a vertical cut that travels from the front of the body to the back, dividing the bioform into left and right portions. In biomechanics, this is arguably the most active plane. It is the primary stage for movements that involve folding or straightening the body. When you analyze a squat, a sprint, or a bipedal gait cycle, you are primarily observing displacement within the sagittal plane. 1. Median mid-sagittal plane. This is the 0 point of the sagittal axis. It passes directly through the midline of the body, creating equal left and right halves. Mechanical significance. This plane is our reference for symmetry. For an engineer, this is the center of mass axis. If a load is offset from this plane, you are dealing with asymmetrical loading, which changes the stress distribution across the entire skeletal frame. 2. Parasagittal plane. Any sagittal cut that is not on the midline is a parasagittal plane. These divide the body into unequal left and right portions. Mechanical significance. We use these when we need to isolate a specific limb or joint that sits away from the center. If you are designing a hip replacement or analyzing the mechanics of a single knee, you are operating in a parasagittal plane, specific to that joint's vertical axis. Associative movement. The sagittal rule. The movements associated with this plane are almost exclusively flexion and extension. Flexion. Decreasing the angle between body parts moving forward in most joints. Extension. Increasing that angle moving backward. The engineer's perspective. Imagine the body is sandwiched between two sheets of glass. If you can perform the movement without breaking the glass on your left or right, you are moving in the sagittal plane. This is the first dimension of our 3D workspace. We'll layer the other planes on top of this to complete the volume. The second dimension of our 3D workspace is the frontal plane, also known as the coronal plane. While the sagittal plane divides us into left and right, the frontal plane is a vertical slice that divides the body into anterior, which is forward, and posterior, which is backward portions. If you think of the sagittal plane as the profile view, the frontal plane is the face-on view. This plane is critical for analyzing structural balance and lateral stability. Associative movements. The lateral rule. The primary movements occurring within this plane are abduction and adduction. Abduction, moving a limb away from the midline. Adduction, bringing a limb back toward the midline. To put that into perspective, if the sagittal plane was about folding, the frontal plane is about spreading. Imagine you are standing with your back against a wall. Any movement you can make while keeping your heels, buttocks, and shoulders in contact with that wall is occurring in the frontal plane. For a medical engineering student, this plane is where we analyze coronal alignment. If you are designing a lower limb prosthetic, any deviation in this plane like a knock knee or boat orientation introduces parasitic shear forces that the materials were not designed to handle. We aren't just looking for symmetry, we are looking for the vertical alignment of the load-bearing axis. To complete our three-dimensional coordinate system, we look at the transverse plane, also known as the horizontal or axial plane. Unlike the previous two vertical slices, this is a cross-sectional cut that divides the body into superior, which is upward, and inferior, which is downward portions. In the context of biomedical engineering, this plane is where we analyze the torsion of the system, while the sagittal and frontal planes handle the levers of the body moving in space. The transverse plane is where we measure how those levers pivot. Associative movements. The rotational rule. This plane is almost exclusively associated with rotational movements. Internal medial rotation, pivoting the structure toward the midline. External lateral rotation, pivoting the structure away from the midline. Pronation and supination, the specialized rotational mechanics of the forearm. To put that into perspective, imagine the body is viewed from a bird's-eye perspective, looking straight down the vertical axis. Any movement that spins around this center point happens in the transverse plane. For your design work, this plane is the most complex to master. If you are developing a prosthetic limb, the sagittal and frontal alignments handle the weight, but the transverse alignment determines the natural gait. If a prosthetic foot is toed in or toed out, just a few degrees in the transverse plane, it creates a rotational stress torque that can lead to mechanical wear at the interface or joint pain in the user. We must ensure the rotational axis of the hardware perfectly mirrors the biological axis of the bone. With these three planes, sagittal, frontal, and transverse, we now have the full Cartesian coordinates of the human frame. Every force vector we calculate from here on out will be referenced against these axes. Beyond the primary coordinate system, we utilize secondary and specialized planes to capture the non-standard geometries of human movement and internal structures. In engineering, rarely does a force act perfectly at 90 degrees to a primary axis. These planes allow us to map those deviations. 1. Oblique plane. An oblique plane is any surface that passes through the body at an angle that is not parallel to the primary sagittal, frontal, or transverse planes. Mechanical significance. Most real-world injuries and complex athletic movements occur in oblique planes. Example, think of a golfer's swing or a pitcher's throw. These are multiaxial movements where the force vector is slanted. When we analyze these, we have to resolve the forces into their primary components, but we describe the path of the motion as oblique. 2. Longitudinal plane. A longitudinal plane is defined relative to the specific structure itself, rather than the body as a whole. It is any plane that runs parallel to the long axis of a structure, such as a bone or a limb. Mechanical significance. This is our reference for lengthwise analysis. When we discuss anisotropy, how bone is stronger along its length, we are referring to loads applied in a longitudinal plane. Example, a cut that runs from the hip to the knee to the center of the femur is a longitudinal section. It is essential for inspecting the internal canal of long bones for prosthetic fitting. 3. Cross-sectional plane. The cross-sectional plane runs perpendicular to the long axis of a structure. This is the slice view of a component. Mechanical significance. We use this to calculate the cross-sectional area, CSA, of a muscle or bone. In structural engineering, the CSA is a primary variable in determining how much stress a material can handle before it deforms or fails. Example, if you slice a bicep muscle or a humerus bone in half to look at the density of the internal tissue, you are looking at a cross-section. By mastering these, you aren't just looking at a 2D drawing anymore. You are viewing the body as a volumetric model. You can slice it at any angle, oblique, along its length, longitudinal, or across its width, cross-sectional, to find the exact data point you need for your design.